Today I'll be giving you a very informal summary of our recent work, Decoupled Embeddings for Pre-training Language Models, which will appear as an oral presentation at ICLR 1025 on the 26th of April at 11:30. I'm Alex. I'm presenting work that was done in a collaboration between Cambridge Machine Learning Systems and Flower Labs, a federated learning startup. And the too long didn't watch summary of our work is, if you separate the transform body from the embedding matrices, you can significantly reduce the communication costs and the memory costs of pre-training. To give a bit of context, we were looking at a very practical problem of achieving federated multilingual pre-training, and we noticed that in such scenarios you quickly run into this issue where if you don't know the data distribution that you're going to be training over in advance, you may end up in a situation where data heterogeneity negatively impacts your model's ability to train. And by data heterogeneity in this context, we mean having languages with different vocabularies and character sets and syntax and semantics, or multi-domain data such as mathematics or code. And in such situations, you can end up with these two very well-known problems of the curse of multilinguality and negative interference, which are essentially this idea that if you keep adding diverse data sources to your pre-training mixture, you're going to get an improvement in performance, then a plateau, and then an eventual decline. Beyond this, we're also observing that our vocabularies for multilingual pre-training were very large, and we did not need the entire vocabulary for many of our data distributions, since we did not have all of the languages in distribution. And that ended up costing us significant in terms of the memory allocation needed for a model. Our solution to this is called DEPT, Decoupled Embeddings for Pre-training. And the core idea is to separate the embedding matrix from the transformer blocks. In this diagram, we have all of the methods we consider in the paper. On the top left, we have just standard DDP, which is sampling at random from all of your data sources at once and having one unified embedding matrix in memory. And then below that, we have globe, which is our starting point. Essentially, it's this federated learning inspired method, which can be applied in centralized context as well, or data parallel context as well, where you take your data sources, you allow them to remain split instead of mixing them, and you train independently on each data source for a given number of local steps before applying an aggregation procedure to obtain one unified model. And starting from this federated viewpoint, transition to the data parallel context, we propose two efficient training methods on top of it. The first is called trim, which is on the top, and it essentially takes the embedding matrix and reduces the vocabulary to the strictly necessary tokens for the given data source. And then this allows you to reduce the communication and memory costs of the model. Then we have spec, which essentially states that if you take the embedding matrix and make it fully specialized to the data source, you never need to share it, as in because only this data source trains with this embedding matrix, you can do the training entirely locally, and then you don't have to ever propagate the information to any of the other embeddings. And both of these methods, because they're built on globe, achieve this sort of linear reduction in the communication cost due to only communicating every n local steps. However, these two new methods further reduce the communication and memory costs of training the model based on the difference between the vocabulary of a given data source and the global unified vocabulary. And in the case of trim, you still need to communicate the embeddings that are shared across all of the different data sources, but for spec, you can completely avoid communicating the embedding matrix. And in both of their cases, you get significant reductions in the VRAM allocation that you need. In terms of results, we observe that our method improves training plasticity. So if you want to adapt the model to a new data distribution, it is going to perform better when it has been pre-trained in this fashion. We observe that we improve downstream generalization in the sense that once we attach an adapter to the model, we can get better downstream task performance by significant amounts, and that it improves training robustness in the sense that during the pre-training stage, the aggregation procedure implicit in these methods causes a reduction in the norm of the model and the norm of the activations, and results in more stable training, potentially due to previously known effects such as noise injection. Our work is available at this QR code.